What if I told you that the light streaming through the trees began its journey over 100,000 years ago? That right now, the sun, 150 million kilometers away, is holding the entire solar system together? And that one day, it will grow so large it could erase the Earth entirely? It's easy to forget the sun is a colossal star, alive with energy, motion, and unimaginable force. An engine of creation and destruction. It's a stellar machine, forged in gravity and pressure. A place where atoms fuse together, where light crawls for millennia before ever reaching us, and where, at its outer edge, a mystery is still unfolding. So how does our immense, powerful star work? Well, to find that out, we need to go deep inside. The sun is just one of hundreds of billions of stars in the Milky Way. But to Earth, it's everything. It breathes life into our oceans, warms our skies, and it stirs the heartbeat of the planet, guiding biology, behavior, and even our sense of time. You could fit 1.3 million Earths inside it, and it's still not even considered a large star. But where did it come from? Over 4.6 billion years ago, a vast cloud of gas and dust collapsed under its own weight. From that swirling chaos emerged our sun, pulling in 99.8% of all material in the solar system. At its core, nuclear fusion ignited and a star was born. This process hasn't stopped since. Every moment the sun fuses hydrogen into helium, releasing light and heat that has shaped every world in the solar system. We can't peer directly into the sun. Its layers are opaque, blindingly bright, and unimaginably hot, far beyond the reach of any probe or telescope, but that hasn't stopped us from exploring it. Using a combination of advanced physics and indirect observation, scientists have built a remarkably detailed picture of what lies beneath the surface. 6 distinct layers, each playing its part in the delicate balance that powers a star. So let's begin at the very center. At the core is the powerhouse, an enormous nuclear fusion reactor. Temperatures here reach 15 million degrees Celsius, 27 million degrees Fahrenheit, at least 12,000 times hotter than molten lava. This is the place where light itself is born, where energy is released every second, greater than 6 trillion Hiroshima nuclear bombs. Think about that, every second. But that light doesn't escape easily. It has a long journey ahead. Surrounding the core is the radiative zone. Here, photons, the particles of light, begin their trek outward. But instead of flying freely, they're absorbed by atoms, re-emitted, absorbed again, over and over. According to NASA, it can take a single photon over 100,000 years to pass through this layer. The light you see today? It may have started its journey when woolly mammoths roamed the Earth. Before being absorbed by your eyes, eventually the light reaches a point where temperatures drop enough for convection to take over. Hot plasma rises, cool plasma sinks, rolling in massive columns much like boiling water. From a telescope, these look like shimmering cells on the sun's surface, the final step before sunlight escapes. But what we call the surface isn't really a surface at all. It shines with the light that took thousands of centuries to reach it. It's cooler than the interior, but still a blistering 5,500 degrees C, hot enough to melt diamond. Sunspots, solar flares, and dramatic plasma arcs all appear here, windows into the turmoil beneath. And if you look closely, you'll see those boiling convection cells, bright centers of rising gas, rimmed by cooler sinking material. But go just a bit higher, and something strange starts to happen. The sun gets hotter. Above the photosphere lies the chromosphere, a glowing red layer laced with spicules, towering jets of plasma that rise like flames and vanish in seconds. Strangely, this layer is hotter than the photosphere below it. The further you go, the more intense it gets. Why? This is one of the sun's great unsolved mysteries. And now we reach the sun's crown, the corona, a wispy, ethereal aura that extends millions of kilometers into space. Seen only during solar eclipses or captured with X-ray instruments, the corona burns at over 1 million degrees Celsius, far hotter than the layers just below. We still don't know why. The leading theories point to intense magnetic activity, waves rippling through magnetic field lines, and countless tiny explosions known as nanoflares, too small to see individually but powerful when combined. From this superheated outer layer, streams of charged particles escape as solar wind, racing outward through the solar system. And when those particles collide with Earth's magnetic field, something extraordinary happens. They paint the skies with light, the aurora. In the vastness of space, our sun is just another ordinary star. But it has one rare feature. A planet with thinking, dreaming life, watching it, studying it, asking where it came from and where it might take us. We are stardust, and the sun is the beacon that reminds us every day of our connection to the cosmos.